Okay, good morning, everyone. All right, so as I said, today we're going to finish up that network topology lecture that we have started in person. So whoever is watching this maybe 10 years after, they know that, well, the first part of that concept was taken care of in person. So that's the nature of this course, is half in person, half online. So that's the way it is. So it's tailored for the people who actually signed up for the course. However, if you are somebody else 10 years from now, you can still benefit from whatever is being said here. Okay, cool. So let's bring up the... There it is. Okay, so this is more or less where we have stopped. I'll enter the full screen. Just a reminder of what the horizontal and, well, vertical or riser idea is. So horizontal runs, what do we see here? Here, what we have here is that main cross connect. Well, it shows main as, you know, this box here is labeled as main cross connect. What is this? This main cross connect is a room within a building where everything comes in from outside. All the phone lines, all the fiber lines, all the whatever communication is being brought in, it's brought into that room. Well, sometimes it is called the electrical room, which is kind of, you know, iffy name, but a lot of people refer to it as such. The other name for that would be a demarcation point. Demarcation is basically means point of entry, all right? So sometimes it's also referred as the demarc. So you can come in to the building if you're working in this type of service. Say, where is your demarc? And they're gonna say, what? Well, where's your electrical room? All right, that's a good place to start. And if the main cross connect is not provided in the electrical room, then you're going to say, well, where are the phone lines coming in, or the lines? Oh, that's the other room over there. Right. So sometimes you're going to have to find that. But people who take care of the facilities, they will know where things are. Right? So the main thing is, here is the main cross connect, and it's also sometimes being referred to as main distribution frame with the acronym of MDF, stands for main distribution frame. That's for the data connections. Okay? Then the main distribution frame will feed one or more intermediate distribution frames, which would be the secondary demarcation points, so to speak. Right? So here's the MDF, which stands for main distribution frame. This one is connected and feeds the IDFs, which are the intermediate distribution frames. This concept can take different shapes and forms. Like, for example, if there is a shopping mall, huge mall, you're going to have one big room where everything comes in, and from there you're going to have secondary demarcation points that feed certain areas of the huge mall. So let's say this could be the main demarc point, and it could feed the second demarcation point that feeds the east part of the mall. And that could also feed another secondary demarcation point that feeds the west part of the mall, and so on. Right? Then later on, from those, you could have secondary demarcation points, like, for example, to, well, huge department store like Walmart, for example. Then it could have another room of its own that feeds all their connections, right? So, but everything comes in here, and the wiring is distributed accordingly as things are organized. Now, it can have a smaller form, like, for example, in Home Depots or Lowe's or Rona's or Home Hardware or huge stores like that. You're going to have a main distribution frame somewhere around where the offices are. Right? Usually it's like, maybe above the offices, or, sometimes you have to go upstairs and sometimes it's on the main floor. And that's where all the wiring comes in. That's where all the, well, the whole, I don't want to say rat's nest, because, well, although sometimes it does look like it. Sometimes it looks nice and clean. All right, and that MDF is going to feed the IDFs, and those IDFs, if you look at some of those stores, if you look around the walls, you're going to see black boxes that are the size of a small fridge, with huge letters on top of them with the markings that says IDF A, IDF B, IDF C, and so on. These are the intermediate distribution frames. What's in that IDF? In the IDF would be on the bottom, usually, would be the switches. Okay? So on the bottom would be the switches. A switch is a traffic controller for the Ethernet communication signal, type of communication. Right? Those switches are fed from the patch panels, and a patch panel is a frame that contains a bunch of jacks, the Ethernet jacks, and each Ethernet jack goes somewhere to the desktop. Okay. All right. Now, there could be one or more switch. Right? If you have more than one switch, then those switches are going to be connected in a certain way. So if there is a 24 port switch, and that area that is fed from this IDF needs more than 24 connections, then you're going to have another switch on top of that. And if there's need for more, you have another switch on top of that. And those switches are going to be connected in a certain way, so those all individual switches make up one huge switch. Now, that cascade of the switches is going to be connected to something that's called a media converter. And the media converter is going to convert all the electrical signals that are coming from all the PCs through the switches, through the patch panels, those switches are going to be connected to a media converter that is going to convert the electrical signals to light pulses. And the light pulses are going to feed the fiber optic lines, and the fiber optic lines are going to be fed to the main distribution frame. So, main distribution frame with the fiber.
Sir,
Hello?
yeah, is it one switch or many switches?
It could be one, it could be many, because the idea of the switches in the IDFs is that the distance between the switch and the whatever PC or something else that needs to be connected to it is less than 300 feet. So those IDFs are going to be strategically placed around the building, so the lines that are running up to it are no longer than 300 feet. But if there is more than one switch needed for that area, then you're going to have another switch on top of that. And if there's more, another switch on top of that to accommodate the number of ports that are needed. Okay? And those switches are going to be connected to each other to make up one sort of virtual switch. Okay? Does that answer your question?
Yes, sir.
Okay. If you need more, just talk to me during the lab, okay? I'll explain it to you more. All right. So there's a main distribution frame connects to the IDFs through the fiber optic lines. And from here, copper, which is the Ethernet cables, are being used to connect things to the PCs. So that's more or less how it works. Now, horizontal runs are all the runs that are going to the same closet, or the IDF, or, well, it could be MDF, right, if there's a small venue. Right? So these three PCs are part of this horizontal connection, this horizontal configuration. Let's say if this PC was connected through the wall, up the ceiling, it goes to that one. So these two would be part of that horizontal run, and this one still, even though it's on the bottom floor, if it's connected to that one, it's going to be part of this horizontal. So here's the horizontal. Yes, the lines are going vertically up in the ceiling, then across, then down the wall. So here's the vertical, horizontal, vertical. So don't pay attention to that. It's the horizontal configuration here. And over here, what we have, most of the buildings are going to have, like right now, if you have buildings that consists of more than one floor, hospitals, business high rises, whatnot, they will have the communication rooms at the same spot. So if you are in one communications room on one floor, you can almost be sure that right underneath you is going to be the communication room for the floor below you, and so on. This is called a riser. That's the riser configuration. It is, the purpose of that is so the running of the lines or wires or whatnot is it kind of makes sense. It's easier to be accomplished. Okay? So that's as far as the horizontal lines and the configurations. Now here you could tell as far as topology, these here 1, 2, 3, those PCs are connected in a star configuration because all the lines, we say it that they home run to this location here. So all these home run, this is the home, and those wires run home. Okay? Now also, just to add to some of the confusion, or maybe not, this would be considered a plenum wiring. Plenum is the space in the ceiling between the ceiling tiles and the true ceiling. That's called plenum. Later on, I'll explain it to you further, but we have closed air circulation or cold air return plenum, and that has to do with the air ducts and how the air is being circulated in the building. And based on that, we're going to have to choose certain type of wires as far as the jacketing goes. FT6 and FT4 rating. It's a fire rating, and FT6 has to be used if it's something that's called cold air return plenum, and FT4 can be used if it's a closed air circulation. I will explain that thing to you further, but I'm just giving you a heads up. If you want to research that further before I explain it to you, that's fine as well. All right, so here's another visual. Oops. Can I do this? Yeah. So this would be as far as what's inside that communication frame or closet, IDF or MDF, depends on how big the building is, right? This would be a bunch of patch panels. From here, from these patch panels, wires run to the desktop, run to location in the field. See, there's a horizontal run, horizontal run, horizontal run, and so on. Okay. Each individual jack. So here's a PC. It has a network interface card. It's connected to the wall plate. From the wall plate, there's a horizontal run that's terminated on the other side of one of those ports. So here's a jack to jack link here. And from here, there's a patch cable that is being connected from that port to one of the switches. So each individual PC has a designated port on the switch. Those switches can be one switch if it's enough to accommodate the number of connections that needs to be accomplished, or there could be more than one switch cascaded together to make one huger, if you will, switch that needs to accommodate all the devices that need to be connected to this particular closet. And those switches, I don't have the media converter drawn here, so those switches could be connected to a media converter, and the media converter would be connected to fiber optic lines that are feeding the main distribution frame somewhere. All right, continue with the topology, bus topology. That's the symbol of the topology. There's one main signal line, and devices are tapped into it. Remember when we were talking about the audio distribution system, it's in a way it is those wires, those speaker stations are connected to the main line because they are just tapped into it, a bunch of parallel connections. It would be something like a bus configuration, right? Now, bus topology was used in LAN settings until the early 1990s. I remember when I was going to college, that was how all our school computers were connected. It would be one coaxial cable with taps, and those taps would just get another coaxial cable to the network interface card that was going to the PC. Now that system was not very fast; was nowhere near as fast as the Ethernet connections that we have. But that's what we had then. All right. Now this thing is all abandoned. Now you're not going to be able to find any. Well, maybe some vintage hobbies. People are. If there's any of that maybe like to get old equipment and make it look like it works for some hobby or sentimental purposes. But in the industrial environment right now, in commercial environment, we don't have those connections right now. Does it mean that the bus topology is out? No, it's not. All right. The bus topology is used in different fields still, in different types of equipment. Right? So I just want you to know what bus topology is. There's one main river, and just imagine it's like a river with the water flowing, and each household has tap into that water, into that river. All right, where do we see the bus topology? Couple of examples. This one is very simple, borderline simplistic kind of setup here. This is how fire alarms are connected, and this is how security alarms are connected. All right, so I'm giving you some real life examples. All right, how is it the fire alarm is connected? Fire alarm sensors are connected to a zone circuit. What is a zone? A zone is a point on the alarm panel that can be triggered. And that point can be annunciated in the annunciator panel, and it could be also named. So if you have a bunch of devices connected to the west hallway or something like that, and those are basically a bunch of smoke detectors that are connected to that one zone. If any one of those gets triggered, the panel would annunciate that smoke detected west hallway. Just kind of pulling that thing out of the air, the names, right? So alarm panels, security and fire alarm panels, they have multiple zones. So the zones can be named. So here is the smoke detectors in certain corridor. Here are the smoke detectors in the air ducts that's going to a certain place. Here is a zone that connects all the pull stations in the hallway that goes from here to there, and so on. Okay? So here is an example of one zone. How does that work? How is that zone being triggered? In fire alarms, things are kind of opposite than in security alarms. But let's take a look at the fire alarm first. A zone in a fire alarm is a loop. It's a closed loop. Those devices are normally open, so the zone doesn't even see them. These are devices. It could be active or could be passive. If it's active, then that device has to be plugged into something, some sort of source of power source. And if it's a passive device, then, well, it is just sitting there with the switch open, so it's not connected. Well, when it triggers, it closes the switch, shorting things out this way here, or shorting it this way here, or shorting it like that. But these are normally open devices. What the zone needs to see in the fire alarm, because if those are open, so you can just imagine they don't exist, because the zone doesn't see them until the switches in each individual close if it detects something that is supposed to detect. Fire, well, smoke, fire, heat. Yeah. All right. So if those are open, they don't exist, sort of. But what the zone wants to see is at the end of the line is a resistor of a certain resistance, and it's closed here. If the zone sees that resistor at the end of the line, and okay, look, it's actually named end of line resistor. This one here is 4.7 kilo ohms. It's a common resistance for end of line resistor for fire alarm. But you know, if you have different panels, sometimes those could slightly vary. So you have to choose the proper one for the proper panel. But 4.7 is a quite common one, right? So when this zone sees that 4.7 kilo ohm resistor at the end, it could be 4.7 plus or minus few ohms, depending on how long that line is, because wire itself also has some resistance. You know, it could give you 2-3 ohms. You know, then if that zone sees that resistor, sees that resistance, then the zone thinks, quote unquote, that everything is okay. If the resistor is broken, if that thing is disconnected, then the zone is going to see an open line. Is it going to trigger into alarm? No, it is going to trigger into a trouble mode, and it's going to produce annoying beeps at the panel, so the people in the office are going to investigate what's going on, why is this thing beeping? And when it's beeping, usually there will be a phone number to call right by the light flashing where this thing is beeping. It says alarm trouble, call so-and-so. So, you know, of course, the people say, okay, fire alarm is beeping, are we in trouble? It says trouble. So they are going to call quite quickly that phone number, and it's, you know, no, this is not a fire. It's you know, it indicates trouble on the detecting lines. We're going to have to come and see what's going on. So don't worry, that's not a fire. Okay, okay. So that's how that thing works. Now, if any of those devices trigger, you're going to see a dead short between here and here. And then if that zone sees a dead short, then it's going to trigger into alarm mode, fire alarm mode, and all that's going to cause all chain reaction of whatnot. So that's more or less, so this would be a bus topology, because these devices are connected to the main line in a bus configuration. There is no any Ethernet communication going on or whatnot. It's just a simple analog zone. Right? Although some of the more modern fire alarm panels, they utilize Ethernet, but up to some point. Now, let's take a look at the alarm security alarm system here. Where is bus topology used in this configuration? We're going to take a look at how the zones work, but these are different. Those zones home run and they are in series, so forget that zoning. It's different than fire alarms, okay? I will explain how later on, but we're concentrating on the bus topology. Now, the wires that are used for the fire alarm, for the most part, for the security alarm, for the most part are so-called Z type of wires and Z4. Z4 is a thin wire with, well, 22 gauge solid conductors in it, and it has 4 conductors, and usually would be yellow, green, black, and red. Okay. Now, when the USOC configuration, which we're going to study later on, probably next week, the red and green is a pair for telephone communications, and the black and yellow is pair number 2 for the telephone communications. But when it comes to Z wires, they also have the same colors. They have those yellow, green, red, and black, but the colors are used slightly different way. For the most part, if it's a power, so it's auxiliary, that's the 12-volt power here, that power is being supplied to all the active devices, like for example keypads, but I didn't draw those wires here, okay? Just to kind of not pollute visually here. What other active devices? Motion sensors, glass break detectors, anything that requires power is getting power supplied from this plus and minus 12 volts DC. But you also have on the main board of the security alarm panel something that is called a bus terminals. This is a type of communication that goes between devices that are connected to it, and see, those are connected in parallel. They don't have individual connections to the individual points, but here is the line that goes all the way as far as it needs to go, and the devices with their signal, that's not power, that's actual signal, the intelligence signal that's going through that, is tapped into that line, you see, in parallel kind of configuration, which means it's a bus type of configuration. How the signal is, and in this way, through different type of modulating of the signal, things are solved that this here can individually communicate with the main panel, and this other device can individually communicate with the main panel all at the same time, but they are on the same line, connected parallel. Modulation, signal modulation, or frequency division multiplexing is being used when it comes to that. It's just like a radio communication. Where would be the main bus connection between different radio stations and radio receivers and walkie-talkie here and walkie-talkie there? Where would be the main line that connects? Well, it's the air. They're using the radios using different frequencies to communicate with other radios, but they're using the same medium, and the whole signal, all the signals are crumbled in the air. So this is just like signals are being crumbled in the air, but it's in the closed environment consisting of two wires. So another example of a bus topology. Now, here, now we're going to go into something that's called a ring or inline or chain topology. Well, inline and chain, not a ring. Ring is different. This is chain. A chain is an open ring. If it would be ring, then that point would be connected back to this point here. But if it's chain, it's just this one here is not connected anywhere. That thing is not connected. It's just a chain. Okay? All right. How are things being connected here? Let me read this sentence. In this configuration, nodes are connected to each other through each other in a chain configuration. All right. Each node acts as a repeater. If this node wants to communicate with that one, that message has to be repeated by this one, it has to be repeated by this one, and it gets to that one right there. Right? And if he wants to answer, same thing happens in the reverse process. All right, so what else did I say here a couple of years ago? As opposed to the ring configuration, the last device is not connected to the first device to form a looped pathway. So here is an example of a ring topology, that this switch, okay, let's say this switch is connected to that switch, and that this switch connected to that switch, and that here, and then loop is closed by going all over. So it's a ring topology. And here's a chain topology. Those switches are connected to each other, but the ends are not connected. So there is no a loop. There is no a ring formation going on. Where is the where is the inline or chain topology being used? Quite often on the production lines, when you have control modules controlling different machinery, those modules, forget the switch things here, those modules will be just connected through Ethernet cable in chain topology, right? So the only disadvantage of that is that if this communication link breaks, right, then the whole communication kind of is stumbling, all right? Which is in ring topology, and if you have a token ring, because in a ring the communication goes only one way, in a token ring the communication goes both ways. So if this one wants to communicate with that one, it uses this link here, but if this link is broken, it is going to try to go around the long way and still can get to that one, right? So token ring, communication goes in. But then again, here's a ring topology, here's a chain topology, that's it, right? Now, let me give you some real-life examples, and by giving you the real-life examples, some of us might discover some types of equipment that is being used here and there. So this way, it's going to build your the collection of knowledge of the devices that exist on the market. And sometimes when you troubleshoot things, you might know more of what's available on the market and how to use that type of equipment. Let's start with a simple thing: inline or chain topology. All right, so here, if you have a switch, different ports, and you have a PC and you have a printer, and those home run to the switch, those lines, the connection from here home runs to the switch. The connection from here, physically, there's a wire that home runs to that. So the PC is connected to one of the ports, a printer is connected to some other port. It is a star topology. But, well, okay, so where would that be used? Well, this would be used in some large office environments where there's a bunch of offices and there's one huge printer or two maybe. So if somebody wants to print something, they send it to printer A, printer B, or whatever, and that thing is being printed. Right? So there's one common printer for a bunch of workstations. Over here, it's a different situation. If somebody really wants to have their own printer in their own office on their own desktop, then you can use a chain topology. So this printer here is connected in line with the PC to the switch. Right? Also, well, let's not get ahead. All right, let's go inline or chain topology. All right, what's this thing here? This one is called Ethernet extender. It extends Ethernet line. Why would we need an Ethernet extender? Well, here's an example. Let's say there is a common place in large department stores, those hardware stores, when they have garden centers, and those garden centers are located somewhere in the parking lot. Some people didn't think about the communications when they're building that. So the idea of the Ethernet line is that the physical link, the physical copper wire, is no longer end-to-end, is no longer than 328 feet. If the wire is longer than 328 feet, then the data, some of the data might get lost along the cable. It's just that this is the distance the cable can, the Ethernet communication can handle, 328 feet at the most. Some of the cables, when it comes to choosing certain speeds, can handle even less distance. But let's say Cat5e typical configuration, no more than 328 feet. However, what we're trying to accomplish is that the link from the patch panel location to the desktop location is no longer than 300 feet. Why not 328? Well, because we still need to use patch cords, and they do add distance. Okay. So a patch cord goes from jack to the PC, to the switch, and the other one jack to the PC, or whatever it is, right? And the PC, in that case, garden center would be the cash register, is the actual PC. So let's say here is a switch in one of the IDFs on the wall in Home Depot, for example, and it is on one of the walls inside the store, and there's a line going either overhead, but most of the time it's going to go underground, and it's going to go right to the garden center. Just before the garden center, there's going to be a pull box coming from the ground, and from there there's going to be another wire going right to where the cash register is. So a real life situation that I had a few times is that, okay, I got a service call that the cash register works intermittently. Sometimes it just say communication broken or something like that, and sometimes it works and there's no rhyme or reason. That tells me that probably that line here is longer than 328 feet. So what I would do is I would just go from, I would put in one of those. You see, when we are testing the wires in the lab, it will be exactly the same tester. I would plug in the end of it to one end, and I'll go with my meter, plug it into the other end, press the test button, and check for the distance. Well, I'm not checking for the distance because the distance is going to be displayed on it, so I'm just going to read what the distance is. And I would say, okay, so here is something like 280 feet from here to here. Okay, and then I go plug it into, unplug that, and I plug in my meter to the other line that goes from here to the PC, where the pull box is on the ground, coming out of the ground. And over here it shows that it's like 50 feet. Well, 290 feet plus 50 feet is going to give me 340 feet, which is more than 328 feet. That's where the problem is. Well, solution. There's a problem, there's a solution. Put an Ethernet extender, excuse me, if you can find that spot. Sometimes, I would be lucky if, but sometimes the wire is just all the way there. Well, we're out of luck. But let's say there's the pull box there. I would put something that's called the Ethernet extender. And, well, the Ethernet extender is going to take care of the less than 300 feet here and less than 300 feet here. It's going to act sort of like an Ethernet repeater. Yes, the communication is going to be slower than if it wasn't here, because things have to be repeated, passed on. From here, things have to be repeated, passed on. So yes, it's going to slow things down. However, if it's something that's like a cash register, we don't care about the speed, because with every connection that the cash register makes with the switch, it's just for the purpose of transmitting a couple of numbers here, few numbers there. Yeah, okay. There's no like a high-speed video going on that you have to display. So who cares about if it's a little bit slower? We won't even notice that, right? But Ethernet extenders can be used. It's a powered device, and the power for the device can be obtained from a power transformer that is plugged into that location and just plugged into here to the device to power it up, or something that's called a PoE, which is power over Ethernet. But the switch has to have those ports that are capable of providing power. So this line, the Ethernet line, carries the signal, and on some of the pins of some of the wires or conductors, it's carrying a power to the device. So you don't need to plug this in. It already gets the power from the Ethernet cord. But as I said, the PoE has to be able to exist, in those ports. Some of the less expensive switches don't have that capability. Some of the little bit more expensive switches have PoE on certain ports, and it's going to say ports 1 to 12 PoE, right? And then the rest of them are just signals. And some of them really expensive of those switches, they will have PoE available on all the ports. So then again, you have to make sure what you're dealing with before you make those connections. All right, now, speaking of PoE, right? Here's the inline or chain topology here. This PoE, okay, so that here, all right, this Ethernet extender is connected inline with the Ethernet link. Okay. Now here, another connection, what did I say? This PoE injector is connected in line with the wireless access point. This will be the wireless access point, which is the Wi-Fi device. All right. Okay, here's a situation. There's a facility that had the network installed a few years ago. And on the meeting, somebody would say, well, are we going to provide Wi-Fi for our clients? Oh, no, we don't need that. Let's just concentrate. We got to deal with the money. We got to save the money. We can spend the money somewhere else. Let's shave a buck here. No, we don't need, somebody's just coming here to buy a hamburger and we don't want Wi-Fi. Who would want Wi-Fi here? Just, people. Well, a few years later, those people find out that everybody else has the Wi-Fi, and some of the young people coming to the other places because they have a free Wi-Fi, and they are not visiting their location because they don't have Wi-Fi. So, and they have another meeting. Oh, maybe we should get a Wi-Fi, right? But the equipment is already installed, and the switches are not, the switches that are feeding all the Ethernet connections in that facility, they are not capable of the PoE because somebody wanted to be, frugal with the money. So because, the switches without the PoE are less expensive. Well, but you still want the wireless access point somewhere in the ceiling in the dining room, for example. Okay, well, what can we do? Well, we buy, how much is a Wi-Fi or the wireless access point? Anywhere from $500 to $1,000 per one. Okay, so, well, let's get one. All right, so we connect that signal line from here to a switch. Oh, it still doesn't work. Oh, because it has to be plugged in. Well, if it's plugged in, some of them come with the transformer, the power transformer or the power supply that need to be plugged in here, and the other part has to be plugged into the 110 hydro regular outlet, right? Well, do we have one in the ceiling? Usually we don't. Well, two ways. Getting an electrician to install a outlet somewhere in the proximity of that so the power transformer can be plugged in there. The power supply can be plugged in there, and it's no problem. But that costs a lot of money. Right? The other thing is to replace the switch with ports that are capable of PoE, but then that opens a whole bunch of different cans of worms because you replace the switch, and the switch has to be programmed. How was that programmed? It already works, everything is fine, but now new equipment here, how things, okay, so that could be a complicated or complex procedure. Well, here's another way of doing things. Here is something that's called a PoE injector. All right. It is an active device. It powers up. It has to be powered, but no problem because that goes in the location of the equipment rack. And the equipment rack has something that's called a PDU, which is called Power Distribution Unit, which is a glorified name for a power bar. So there's going to be at least one or more free outlets that this thing can be plugged in, so no problem. And it has two Ethernet ports right here. One port goes to the switch, one of the ports of the switches that is capable only signal, no power over Ethernet. The other one here, now inside that port here is provided with PoE. So the PoE is injected in that line here, power. So from here on, we have a signal traveling from that port with the power injected by this Ethernet PoE injector. So now we have power and a signal. You can plug it into the Wi-Fi device or wireless access point, and everybody happy. Okay, there we go. So this PoE injector is connected with the wireless access point. All right, now here's another example, real life example, and that's being used in huge department stores, like for example, Home Depot or so on. I use Home Depot a lot. Okay, and I'm not associated with any of those places. All right, inline chain topology. Let's say this VoIP telephone set is connected inline with the workstation computer. Quite a popular way of connecting things in huge department stores like Rona, for example. All right. What do we have here? And some of the offices as well. Here we have only one network jack at the location, but we need to connect two devices, VoIP telephone, which is a voice over IP telephone, and a PC, which would be like cash register. So we have those telephones that have two ports in them, input and output. So we can put that in line with the PC. And from that one network connection, the phone is going to grab enough, it has enough traffic there, enough bandwidth that the telephone can grab its own signal and the PC can grab its own signal all from that one wire, and things are working just fine. So if you're working in any one of those stores, just don't go behind the desk and try to disconnect the wires to see how things are connected. But if you can just take a peek. You can walk around and you can see that the VoIP telephones are connected to the jack, and from the phone it goes to the PC, which is the cash register. Very common situation, extremely common situation. One last thing, almost. Let's see here. Consider PC 0, 1, and 2. Here's PC 0, 1, and 2. What am I trying to say here? Are these PCs connected to the switch in the ring configuration, or is it a star? Now, this is a philosophical, hypothetical situation that I'm going to explain to you. You are not going to encounter this type of situation at work. However, this helps with better understanding on the differences between the physical and the logical topology, okay, or the logic topology. All right, now, are these PCs connected in a ring configuration, or is it a star? All right, so here, okay, through this switch. Yes, physically, they're connected in a star configuration to this switch. This goes here, there's line here, there's line here, there's line here. All right, but physically it looks like it's a star configuration, and it is. Can this system work as a ring? And if so, then how? Well, yes, it can, hypothetically, philosophically, right? All right, let's see. Here's a switch, and here are a bunch of PCs connected to the switch, each to individual port, and it's a star, physical topology. Now, logically, hypothetically, philosophically, can be either or, because this can be a star or can be a ring depending on the switch configuration. And if the switch is configured to direct the traffic in the star topology between those PCs, then it's going to be physical and logic star topology. But if you have the physical star topology here, and if the programming of the switch here inside routes the system in the ring configuration, then it could be a physical star and logical ring configuration. Again, you're not going to encounter any of those challenges, but it helps you understand things better. All right, how would that work? Like this, right? In a ring here. If you look at it closer, this thing would be a logical ring and physical star. Right? Okay. Lab foundation. Well, might as well go through that. We're not going to go through the 25 pair. Next time we see each other, we're going to look at the 25 pair, which is fine. Now, here's a patch panel. Here's a jack. This is what we're dealing with last week and this week, so it's a bit of a refresher and a closer look at things. Here's a jack that goes in the wall at the desktop location. There's a bunch of jacks that are mounted on the patch panel, and the patch panel is inserted into something that's called an equipment rack. It's called 19-inch rack, and I'll show you what 19-inch means, because basically it's 19 inches from here to the other end. It's a standard. Why do we use the frames? So we could put all bunch of those jacks together in more compact situation to save space and make heads and tails out of things. Those here can be mounted on the walls, in the walls, at the desktop, under the desks, on top of the desks, in the ceiling, wherever they goes in the field wiring. Right? Configuration. We were going to talk about what T568 is, but this is the color code. This jack has this type of a sticker, and let's say A or B configuration. So if it's A configuration, these two would be orange pair, and these two would be brown pair, for example. So here would be, this one here would be stripe, orange stripe, and this connection here would be orange solid, and over here brown stripe and brown solid. And on the other side, who knows, because this we can see the sticker. Now, at this point, everything is the same. It's a standard. Pair number 1, which is the two middle prongs, is going to be the pair number 1. Pair number 2 is Hags pair number 1, which would be the second pair. And depending, if it's A configuration, the second pair would be orange. If it's B configuration, the second pair would be green. Okay, and then pair number 3 and pair number 4. So remember the dance: 1, 2, 3, and 4. Yeah, okay, there we go. So now, on the other side of this patch panel, you will have some sort of stickers or some sort of way of showing what the connectors are and how they correspond to the jacks. Excuse me, my throat is getting dry. We're almost done. So each patch panel, depending on who made it and how, you're going to have to figure out, just stop a second and figure out how this thing is done. So those color codes are going to be on the other side, and there'll be 4 pairs that correspond to that jack. There'll be another 4 pairs correspond to another jack. So that's how things are being solved here. Now, differences between Cat5e, physical differences between Cat5e and Cat6 data cable. They look almost the same. However, they're a little bit different. Cat5e, you have 4 pairs: blue, orange, green, and brown. Notice that the twist at the Cat6, because Cat6 is more advanced, the twist is tighter in Cat6 than Cat5. The pairs are being twisted at different rate to prevent such phenomenon as crosstalk, and we will talk about that next week. Also, in order to eliminate the crosstalk, and in order to eliminate the crosstalk more efficiently, Cat6 has a little bit more. Yeah. First of all, twist is tighter and more uniform. But it also, Cat6 has a plastic separator. It's just like a crisscross type of a thing. It has a groove here, and it has a groove here, has a groove on the other side, has a groove on the other side. And that separator, with its grooves, it's also twisted as it goes along. So the pairs have their own twist. And again, there's also a twist that the pairs twist around each other, because that here separator, its grooves, twist as it goes along. So the one big thing you're going to see, aside from just, if you just, after a while, you just touch that with your hand and it's not Cat5e, right? It's got to be Cat6. Also, it has that separator in there. Insulation displacement connection. I explained that I keep explaining that thing during the labs. So here you can read that a little bit. One thing I'm going to just mention that, and I was going to correct that, but I decided to keep it just so I can explain things. The insulation displacement connection, in short, it's a connection that's being made by the connector biting into the insulation and making contact with the copper conductor. For that, we need to position that conductor on top here and use a punch tool to push that in. Yeah. Notice that this here, I got it from somewhere on the internet. There's a reference provided. It shows a stranded wire there. That IDC, insulation displacement connection, is not meant for stranded, because as you push that in, that connector can break some of the strands, which is going to make the cable not as efficient as it should be, and things can break away. So there's a mistake here, but I kept it just to show you. IDC doesn't like stranded conductors. It's meant to be with the solid core conductors. And that's the last slide. Well, we got 5 minutes to get to your next class, and that's as far as we went with this thing here. And next week we're going to take care of the USOC, Universal Service Order Code, POTS, and the idea of 25 pair color code. Okay. Thank you very much, ladies and gentlemen, and I'll see you next week.